So we will be starting with the NAND gate and we'll see the modalities of NAND gate, how to create a NAND gate and in particular how to compute the power. So I'm sharing my screen. If you can please see, I'll be starting from that particular library from where we started. So click on the folder in which you started, open in terminal. Let us wait for the terminal. So here the window is being opened. Okay, so file, open your library, and here from here we can open, we'll be starting with the new cell view in our library. Let's call it NAND 1 schematic. So there we are. We'll be starting with uh, NAND gates. This is my NAND gate 1. This is my NAND gate 2. I'll be connecting these NAND gates. This NAND gate will be connected to ground, but remember I haven't connected this substrate to this. I will be connecting this substrate with ground separately. Now I will take the PMOS. There you have PMOS 1 volt. First PMOS, second PMOS, connecting the sources. Here to connect the VDD, then connect here with, and there you get the output. And there you have the first input, and there you get the second input. Okay, so I'll be connecting the pins. The first pin is VDD right here. The second pin is ground there. The third pin is first input A. Let me connect it here. The second input is B. And I'll copy this, select, press C, select, bring it here. So we have B. Or the other way to connect is you can take the wire from there to this. This again is B. And the last one is we have We need to see the direction. Put there, right? So, okay. So one thing which is left that I need to connect this wire substrate with ground, right? Now please see, there is no error. I would be going to launch ADL. ADL is, I want to do the transient analysis for say 60 nanoseconds. Apply. And I want to take the voltage as X, and that is the value of X is 0.8 volts. Apply. Right. Now I'll come here. My first input is VDD. Now I have given the voltage X, which is 0.8 volts. Second is ground. Ground is obviously 0. Okay. Now these two inputs, A and B. Today I'm going to tell you how to take A and B. Now we'll take the function bit. The one value is 0. Sorry, the one value is X. The 0 value is 0. The rise time is 1 femtosecond. Fall time is 1 femtosecond. Period is 20 nanoseconds. And the pattern parameter data, the pattern that I want is 1010. This is for A, right? For B, again the one value is X, the 0 values is 0. Rise time is 1 femto, fall time is 1 femto, period is 20 nanosecond, and the pattern is 1100. Okay, so now the output to be plotted, select on design. This is A, this is B, and there you have V out, right? And we'll be simulating it. Let us see the outputs. You see, there you have A and B, which is for 20 seconds, this is 1, 1, the output is 0. Then this is 1, 0. This is, sorry, this is 0, 1. This is 1, 0. For 1, 1, I need to take it to. So you see when you have taken it 1, 1, it says for, this is for 1, 1, it says 0, right? See, this is 1, 1, it is 0. For 1, 0, 0, 0, 1, this is 1, 0, this is 0, 0. This is a whole NAND gate that you have done over here. Right now, I wish to compute the power consumed in NAND gate. The process remains the same, and I will also looking to compute the delay between input and output. So what is the output for power? For power, you need to do the same process. All, this is apply, okay, and then you'll run it again. Then you'll go to the ADL tools, result browser, tran, power, calculator. In this calculator that you see in the functions, all functions, you please select the average. There you get the average. Then press this button. Once you press this button, you get the power over here. You can write power, right? And now when you run it again, you will see the consumed power 4.016482 nano watts. But it is the true power that you wanted to see. The answer is no. What is the true power? The true power is that I wish to see that, I can show it to you. This is the power consumption, and we'll go to the calculator again. There you have this, and then you take the average. Now, if you don't take the average, you see this. Please see this power consumption from 0 to 20 nanoseconds. The power consumption is in picowatts. Then from 20 to 40, it's in microwatts, right? From 40 to 60, it's again in nanowatts. And then 60 to 80, it's again in picowatt. What is the reason? The reason is the discharge of the data and the switching. Now we'll see the power consumption without switching. How we'll see? We will not give it to the bit, we'll give it to the DC to A. Let's say we'll take the case of 0, 0 on A and B, right? Now, if you run this, the power consumption is 896.90 for 0, 0. It is 896.90 femtowatts. Now we'll see for 0, 1, 1, 0 and 1, 1. See, for it's for 0, 0. Now I'll go for the 0, 1. This for A is for 0, B is for 1. For 0, 1, the power consumption is 2.730 picowatts. Now we'll go for the 1, 0. It is 2.54 picowatts. And now we'll go for 1, 1. And I assume that power consumption should be high here, because for 1, 1, both NMOS will be on and more current will be flowing. Now this is a case of 1, 1. And there you see the consumed power. It is 4.833 picowatts. So the maximum power consumption is during the 1, 1. So the question is, then when you took all the four together, if power is in picowatt or femtowatt, then when you took the power in all the signals together, why the power consumption was high? This is due to the switching power. When you do switching, both PMOS and NMOS get turned on for momentary, which is called the short circuiting. And this, due to switching and short circuit power, the power consumption was high when I took all the bits together. But when I take it bit by bit, then we see the power consumption is pretty low. However, the power consumption is maximum for 1, 1, less than that is for 0, 1, 1, 0 is lesser than that, and 0, 0 is the minimum. And if you take all of them together, the power consumption will be pretty high. This will be because of the switching power which is being used, right? In the next class, we'll see how to go with the delay, right?